Okay, hey guys. So today we'll cover alcohols and carboxylic acids under the organic chemistry syllabus. So under this, we'll cover the properties and chemical reactions of alcohols, and there's a very small segment under carboxylic acid, so we'll cover that very quickly. So we'll just bunch these two chapters together. And as usual, I hope you've been understanding the other chapters and also the other subjects. And if you have any questions, as usual, just feel free to drop them in the comment section, and maybe I'll get back to you as soon as possible, or one of the other people on the internet will get back to you as well. So let's carry on. Give me 1 second. Okay, so properties. The first thing we need to know is that the general formula is CnH2n plus 1 OH. And for naming this, we first understand that we need to find out what the longest carbon chain is. So for this molecule over here, so it's 1, 2, 3. So the longest carbon chain is 3. So we have the word which we use here will be prop. If it was 1, it would be eth, or 2 would be ethane, eth from ethane. So the OH group over here is on the second carbon, so it's propan to all, and the 2 indicating where the OH hydroxyl group is attached to the carbon. So they can form primary, secondary, and tertiary alcohols. So primary alcohol, it will be like RCH2OH. So you could talk about it in terms of hydrogen attached to the carbon molecule. So for example, over here, this is a tertiary alcohol because for this, there's no hydrogens attached to the carbon, which is also attached to the OH. So this will be a tertiary alcohol. And the boiling point is greater than other organic compounds because it forms hydrogen bonding between alcohol and water molecules. So it is also a liquid at room temperature. And then to show that it dissolves in water, this has been tested in one of the past papers. So I'm just showing you the diagram on how to draw it. So the hydrogen bond will be between the lone pair of the oxygen and the hydrogen atom, and it can be from the alcohol molecule to a water molecule, or it can be from a water molecule to the hydrogen, which is attached to the OH bond. So let's carry on. So combustion. So this is quite simple. So it just converts alcohol plus oxygen to carbon dioxide and water. And to balance this, so 2 carbon over here will go to 2 carbon here, and then 6. So 3 times 2, and then you balance the oxygen. So fermentation of alcohol. So just take note, this is only for ethanol. So the reagents which we'll use for this is glucose and yeast, and the conditions will be warm, but which is not more than 37 degrees. It will be anaerobic, which means absence of oxygen. And the equation for this is C6H12O6, which is glucose, which is converted to 2 molecules of C2H5OH, which is ethanol, and 2 molecules of carbon dioxide. So hydration of ethene, is how we convert alkenes to alcohols. So a reagent would be an alkene. Conditions H3PO4 catalyst and high temperature and high pressure. They will accept a range of temperatures and pressures. So I've just given an example of what you could use, but I think they would accept high temperature and pressure by itself. So this reaction converts an alkene. So we'll take example of ethene to an alcohol. So C2H2 to C2H5OH. So this is a type of reaction which we have already studied. It's electrophilic substitution, which is under the alkenes chapter. So if you can't remember this, I've included a diagram here, which will help you understand. So first we need to understand that the oxygen atom on the OH bond is electronegative. So it'll pull the electrons towards itself, which will give it a partial negative charge. And the hydrogen atom over here, which is part of the water molecule, will have a partial positive charge. So the first bond that we have to draw is from the double bond of the alkene to the hydrogen atom, which will produce a carbocation and an OH minus ion. So the OH minus ion has a lone pair, which will form a bond. So we draw an arrow from the lone pair to the positively charged carbon on the carbocation, which will produce CH3CH2OH. Okay, so I hope you understand this. And if you have issues with previous chapters, for example, alkenes, so you could go and rewatch that chapter or read through the textbook one more time. So let's move on. So the next reaction we'll talk about is how we have just added water. We'll talk about how you can remove water. So we use the reagent of concentrated H2SO4, and the conditions that we use here will be high temperature and heating under reflux. This will convert C2H5OH back to C2H2, and will also produce water molecule. And also alternatively, you can also use Al2O3 catalyst and heat. So let's move on. So this is converting and and a haloalkane to an alcohol. So for this, I've taken the SN2 mechanism, but you can also use SN1. So I've just given an example. Okay, so this will involve haloalkanes. So let's take an example of CH3, CH2, CH2Br, and NaOH, which must be dissolved in ethanol. And the conditions are heat under reflux. And if you can remember, this is an nucleophilic substitution covered in the haloalkane chapter. So again, if you can't remember that, go watch the video again. So the first thing we need to do here, okay, so this is the SN2 mechanisms that I was saying. So the OH molecule and the Br molecule will form and break bonds at the same time. So OH minus lone pair will form a bond with the partially positive carbon, and then this will form a intermediate with two bonds which are breaking and forming at the same time, and resulting in R CH2OH, R being this entire side chain. It's not really relevant, and then a Br minus ion is liberated. So let's move on. Also take note that alcohols can react with sodium metal. It will produce a sodium alkoxide, and it will produce hydrogen gas. And note that the hydrogen gas, it can be used to test for presence of OH bond. So to test for OH bond, you basically use lighted splint, and then you put in a test tube with the hydrogen gas, causing the splint to be extinguished, and it will produce a pop sound. And also take note that the hydrogen gas does not itself just say that it's alcohol, because OH bond can be present on both carboxylic acids and alcohols. And the next thing which we have already learned is esterification. So it's a reaction between acids and alcohols to produce ester and water. The reagent is concentrated H2SO4, and the condition is heating under reflux. So take a note that this is a reversible reaction, and we talk about this in the hydrolysis. So the hydrolysis of esters. So since it was a reversible reaction, so you can add the ester and water together, and you provide an acidic environment. So say concentrate H2SO4 as well for the backward reaction, and then heat under reflux, and you'll produce the methanol and ethanoic acid back again. And naming esters, so you need to take note that the alcohol is named first, followed by the acid. For example, butyl propanoate is made from butanol and propanoic acids. And uses of esters, they're used for perfumes, fragrances, and flavoring. You can also do base hydrolysis by NaOH, but take note that once you break the ester linkage, I'll just go back here. So what you have here is CH3C double bond O, and then the acid part will react with the excess sodium hydroxide. So it'll produce O minus Na plus, and it'll produce a sodium ethanoate and CH3CH2OH. Okay, so I just given two examples of naming esters. So I would like you to try this by yourself, and then I have also given the answers here. So I'll just give you a second to look at the diagrams and think about it yourself. Okay, so we look at this right side here. So CH3O, so this is definitely the alcohol. So methanol is the alcohol. So methyl propanoate, 1 plus 2, so 3 carbons, propanoate. Over here, 2 carbon. Okay, so I think I made a mistake here. Right, I think it should be the other way around. So it's a 2 carbon alcohol, and oh wait, no, it should be a 2 carbon alcohol and 2 carbon acid. So it should be ethyl ethanoate. Right, so this is wrong. So it should be ethyl ethanoate, not propyl. Okay, let's carry on. So halogenation of alcohols. So there's 3 ways to do it. It involves 3 different reactants, which is PCl5, PCl3, and SOCl2. And the conditions vary for all these 3 reagents. So let's talk about PCl5 first. So with PCl5, we use room temperature, and it will convert the alcohol into a haloalkane, so C2H5Cl, and it also produces HCl and POCl3. With PCl3 and warming, you produce C2H5Cl and HCPO3, and SOCl2 will produce C2H5Cl again, HCl and SO2. So HCl in this case will be an acidic gas which we can use to test for hydroxyl groups, because it produces steamy fumes. So you can put that as an observation of these reactions. Okay, so for domination and chlorination, it's a bit different. So you can use PI3 and PB3. The reactions are the same. So the reaction in the end is the same, but the reactant is formed using in situ, which is within the reaction using red phosphorus and bromine and iodine. So it's the same equation as this one. So it's the same. Okay, let's carry on. So oxidation of alcohols. So like I was saying, we have to think about whether the alcohol is a primary alcohol, secondary alcohol, or tertiary alcohol before we think about what's the final product. So primary alcohols, if you oxidize them using an oxidizing agent, so in this case, it'll be K2Cr2O7, and you have to acidify. So you could put dilute H2SO4, for example, and it will be oxidized to aldehyde, and then you can heat and distill it to obtain the aldehyde. But if you want a carboxylic acid, you can heat it under reflux. Secondary alcohols, if you heat them under reflux with the oxidizing agent, you'll produce a ketone. And tertiary alcohols, note that you won't have any further oxidation, so you can differentiate between primary, secondary, and tertiary. So this will be mostly for primary and secondary together, and tertiary, so you can only identify tertiary from this. So let's carry on. So what are aldehydes, ketones, right? So aldehydes and ketones are carbonyls, which we'll cover in the next chapter, but I'll just talk about their functional group right now. So this is the alcohol we're talking about. So R, which is the side group, so it doesn't really matter here, CH2OH. So if you form an aldehyde, it will basically form R, C double bond OH. And then if you form a carboxylic acid, this OH becomes oxidized to a hydroxyl group. Ketones, you lose the hydrogen and you form a double bond O, so ketone. And then, like I was saying, tertiary alcohols will have no further oxidation. Let's carry on. So let's talk about how we have learned to synthesize carboxylic acids. So first of all, nucleophilic substitution of CN minus ions. This was done under haloalkanes. So you form a nitrile using KCN in ethanol, which reacts with the haloalkane. So for example, we take CH3CH2CN and we hydrolyze it with HCl and H2O. It will produce CH3CH2COH and then H4Cl. So also take note that this will result in an increase in carbon atoms. So if you're going to synthesize a carboxylic acid, you see that, oh, there's an increase in one carbon atom. That's mostly because of the presence of a CN. So for example, let's take chlorethane as a starting reactant, then it'll become a propane nitrile because there's 3 carbons. So 2 carbons here replaced with a CN. So over here, there'll be 3 carbons, and then the CN will be hydrolyzed to form a COOH. So propanoic acid is formed in that. And also we can oxidize primary alcohols, which we just learned like 20 seconds ago. And lastly, these are acids, so they can react as acids. So they dissociate to form negatively charged ions. And this is quite straightforward, so I'll just let you read this off from the textbook. So I'll just make a quick summary. So they can form salt and water with alkaline solutions. Hydrogen gas and salt is liberated with metals, and salt water CO2 with carbonate. So this is quite straightforward. We have already learned this in our past syllabus. So last reaction that we need to know for carboxylic acid is reduction. So we use this compound called LiAlH4. It's a reducing agent. You don't need to know the full lithium tetrahydroaluminate. You don't need to know that. Just you can write it as LiAlH4. And you could say that it must be dissolved in dry ether because LiAlH4 will react very violently with water. And the entire reaction will occur under room temperature. And since it's a reducing agent, it will provide the hydrogen atoms. So simply, if it's a reducing agent and it's a reduction reaction, the CH3COH will react with 4 hydrogen because gain of hydrogen is reduction, right? So CH3CH2OH will be formed. So we are going back from ethanoic acid to ethanol, and H2O will be formed in the process. Okay, so the oxygen from here will be liberated, and then it'll react with 2 hydrogen to form H2O, and then 2 hydrogen will come in its place, and 2 bonds are free for carbon to react with. So let's cover some questions to fully summarize this chapter. and to test your knowledge of whatever you've learned. So this is a question from the past year paper. It says, which two compounds can react together to produce an ester? Okay, so this is the skeletal formulas of compounds. So let's look at A first. It's a reaction between a alcohol and a ketone. So will it react? No, it won't. It won't produce an ester together. B is alcohol and aldehyde. C is alcohol and carboxylic acid. So C will react, and take note that there's 3 hydroxyl groups, right, or alcohols. So it can react at any part. So ester bonds can form at any part. And this last one, it's an aldehyde and carboxylic acid. So it definitely won't react. So A, B, D is out, and the final answer will be C. Okay, let's talk about this one. So propanoic acid occurs naturally as a result of bacterial fermentation of milk and is partly responsible for the flavor of Swiss cheese, and they're given propanoic acid's formula. So which starting materials can we use to produce propanoic acid? So what's the first compound? The first compound is a 3-carbon alcohol. So propanol. So propanol will react with K2Cr2O7 to produce propanoic acid. So there's a mistake here. So it should be propanol, not propan 1, which is wrong. Sorry, this is propanone. So the second part, it's a 3-carbon compound as well, and this is an aldehyde, so it's propanol. Propanol will also undergo further oxidation to produce a carboxylic acid, and the last one, it's hydrolysis using HCl. You hydrolyze the nitrile to produce a propanoic acid. So there's 3 carbons here, 1, 2, 3, and propanoic acid has 3 as well. So the last one will happen. So all 3 are correct. Okay, let's talk about this one. So propan-2-ol undergoes many reactions. Which row is correct? So reagent added to propan-2-ol. So acidified KMnO4. So what is acidified KMnO4 used for? KMnO4 is oxidizing agent. So this is an oxidation reaction. So if you add an oxidizing agent to a secondary alcohol, propan-2-ol is a secondary alcohol. Draw the structure, you'll understand. What will you produce? You'll produce a ketone, not an aldehyde. An aldehyde is produced by primary alcohols. So if you add Cl2 to propan-2-ol, this formula is correct, but the thing is, the reagent used is wrong. So you must use PCl3, PCl5, those ones, IsoCl2, those are correct. So 3, concentrated H2SO4. So this is an elimination reaction or reduction, and it does produce CH3CH, CH2. So a carbon-carbon double bond is formed. And last one, methanoic acid, esterification reaction. So the formula of the product is incorrect. The OH of the alcohol, the alcohol formula over here is 3-carbon. That's correct. But the thing is, this is propan-2-ol. The reaction over here, the formula shows that the compound is formed from propanol, which with the carbon being on the first carbon. With the alcohol group being on the first carbon. So that's wrong. So the correct answer for this will be C. Okay, so ignore ignore reaction 6 for this, and let's talk about reaction 1 and 2. So the question asked about the type of reaction and reagent conditions used for 1 and 2. So reaction 1, that's electrophilic addition. So it's not supposed to be electrophilic substitution. Electrophilic addition. So this is an alkene becoming into an alcohol. So what do we use here? So H3PO4 catalyst, 350 degrees Celsius and 100 atm, and ethene, which is the alkene. And reaction 2 is oxidation, which converts ethanol into ethanol. So over here, if they ask you for the conditions as well. So you need to write that you heat and then you distill to obtain the aldehyde instead of the carboxylic acid. So I think that summarize everything for these 2 chapters. It's quite straightforward. Carboxylic acid is a very small chapter, and alcohols does require a bit of revision to get a hang of all the reagent conditions. So if you have any questions, leave them in the comment section. If you feel that this video was a little bit fast, you could rewatch the video and maybe get a better understanding. And I hope that this new format of having some questions at the end was also quite helpful. And if you have any suggestions on how you'd like the sessions to improve, you could always leave that in the comment section as well. And as usual, I hope you've been finding the lessons useful. And that'll be all for now. I'll see you in the next video. Thank you.